All right, guys, today we are going to finally get into some of the shortcuts when we're taking derivatives. I guess just some rules that make this formula something we don't even have to use anymore. There are times that it's going to come up, but for the most part, we can put these rules together and come up with the same answer without having to go through all of this algebra. Instead, we're going to do different algebra. So the first rule that we're going to talk about is the constant rule, which is, I'm not going to spend a lot of time on it because it's really simple. The derivative of a constant is 0. So if your function is just a constant, then the derivative is 0, which makes sense because right here we have a function that's a constant, whatever c is. This might be f of x equals 7. So no matter what x goes in, I have a straight line. Well, because I have a straight line left to right, it's a horizontal line, my slope is always going to be 0. So f prime of x is always 0 when you're dealing with a constant. So if y equals 4, the derivative is 0. If s of t equals -8, the derivative is 0. If y equals pi times e squared, well, that's a constant. That's a constant. So the derivative is still equal to 0. So now the power rule. If f of x is equal to x to the n, and this is one that some of you have kind of started picking up as we were doing these problems in the last homework. If this is our function, if it's something raised to a power, then f prime of x is equal to, we drop that power down in front and multiply by it, and then we lower our power by 1. So for example, x to the third right here, I would take that 3 and drop it down to front. So f prime of x equals, that 3 gets down and multiplied in front. I still have my x, but instead of x to the third, it drops down to x squared. Okay, and this works all of the time when we're dealing with exponents. X squared, that 2 drops down. So f prime of x equals 2x. And instead of a 2, this drops down to a 1, which we don't usually write. We would just leave it as 2 to the x. And then like f of x equals x to the first power. So f prime of x is going to equal, if I drop that 1 down in front and then multiply by x to the 0, then I'm just left with 1. Because x to the 0 is 1. Now we've got to be careful because this rule carries over when we have fractional exponents. So for example, f prime of x equals x to the half. That 1/2 is still going to drop down in front. And I've got x, but when I minus 1, this becomes -1/2, which I can rewrite this one. The 1/2 can be written as 1 over 2. And x to the -1/2, remember, to get rid of negative exponents, you can move this entire thing to the bottom. So this can become x to the +1/2. And if you wanted to write it and get rid of exponents completely, remember this could become 2 root x on the bottom there. F of x equals x to the 4th. Same idea. F prime of x equals, the 1/4 comes down, x stays there. I've got to do 1/4 minus 1, and that becomes -3/4. Wow, that color is not easy to see on the green. Sorry. So we've got 1/4 x to the -3/4. Now I can simplify the 1/4. That's just 1 over 4. And the x to the -3/4 can drop to the bottom and become x to the +3/4. And if you wanted to get rid of the exponent, again, you could do 1 over 4. And remember, to get rid of my fractional exponents, I move the bottom of the fraction, becomes my root, and the top stays on the inside, x cubed. One more, f prime of x equals, that -1 comes in front. We get x to the -2 on top. So when I simplify, that's just -1 over x squared. All right, moving on. Using the power rule. So we've got to be careful about using the power rule. There's a few things that have to happen. First of all, you can't use the power rule without an exponent. So you have to have an exponent. You also need it to be in the numerator. So not only do you have to have an exponent, but it needs to be in the numerator. So we can't have an exponent in a denominator. So a lot of problems you can just rewrite and still use the power rule. X to the first power, well, that's just the regular power rule. That's just x to the first, and when we differentiate, we get 1 times x to the 0, which is just 1. Okay, but for root x, we have to rewrite. And remember, to get rid of this 4, I put it on the bottom of my exponent, the bottom of the fraction. So this is technically x to the first power. So that 4 just moves to the bottom. And then when I differentiate, we did this one, right? That's 1/4 x to the negative 3/4, because I'm minus 1 times by 1/4. And when I simplify, I get 1 on top, I get 4 on the bottom, and the x to the 3/4. And like we did before, I can take this fractional exponent and turn it back into a radical by moving the 4 to the root and leaving the x cubed underneath. Although either of these I would count as the correct answer. Okay, let's do one more. 1 over x cubed, like we saw in the last slide, I just have to move this x cubed to the top. And to do that, I need to change it from a positive exponent to a negative exponent. So when I differentiate, I multiply by the negative 3. X, be careful when you minus 1 that you go to negative 4. And when I simplify, that becomes negative 3 over x to the 4th. So make sure your numerator is on, or your exponent is on top. And of course, the power rule only works when you have a power, which makes sense. Multiplying by a constant. A lot of times you kind of just do this naturally, but there is a rule behind it. What it's saying is if I take the derivative of some function with a constant being multiplied in front, I can kind of pull that constant out and do the derivative and then multiply the constant back in. So instead of the constant being part of the function, you can pull it out, derive the function, and put it back in. So for example, this 4x cubed is really 4 times x cubed. So if I differentiate the x cubed part, that becomes 3x squared, but I still have this 4 out in front. So that just becomes 12x squared when I simplify. I tend to just do this naturally. I tend to just take the 3 and multiply it by the constant to begin with. But there are times that it'll be easier to pull that constant out front. I'm not going to do all of these examples, but just to show you a couple of them, let's go ahead and do this one right here. So this is basically 6 times 3 root x, which doesn't work yet because I don't have, I can't differentiate this until I move it up into an exponent. So that becomes 6 times x raised to the 1/3. So when I differentiate, I get 6 times 1/3 x raised to the negative 2/3, because I minus 1, moved the 1/3 in front. So now when I multiply, when I simplify, 6 times 1/3 is 6/3. And x to the negative 2/3, well, I guess we can move that to the bottom, and 6 over 3 just becomes 2. So this becomes 2. And the x to the negative 2/3 can go to the bottom and become positive 2/3. And again, if you want to switch it to radical form, that would be 2 over the cube root of x squared. Okay, so sometimes it's easier to just multiply it in. That one, you could have done the same thing. You could have just done 1/3 times 6 in the very beginning. Whatever works for you. Let's do a couple more of these really quick. I think we've got some time. So how about this one right here? G of x is negative 2 times 1 over x, which we're going to rewrite again to be negative 2 times x to the negative 1. So when I differentiate, g prime of x is going to equal, I've got the negative 2 in front, The -1 multiplies down, and then it becomes x to the -2. And when I simplify that one, -1 times -2 becomes a +1. And the x to the -2, I can move to the bottom and change it to x squared. Oops, +2. I wrote a +1. Don't do that. Like something doesn't look right. There we go. Okay, we've got a couple more. If you want to see these examples, you can try them on your own. Actually, you know what? Let's do this last one. Let's find the f prime of x of this last one here. So if I rewrite this, it's just 2 multiplied this 3x to the third. Before I move it up, I'm going to take that 3 and distribute that exponent. So basically what it becomes is 2 over 3 cubed. Everything's being multiplied, so I can just multiply that. So 3 cubed is 27 x cubed. So when I rewrite this, it's actually 2 over 27. And my x, to move it to the top, I've got to make it a negative. So now when I differentiate, the 2 27ths can kind of just sit there for a minute. They're going to multiply by that -3 that's going to drop down. And this is going to be x to the -4. So when I simplify, -3 times 2, that's -6 over 27. And then I'm left with this x to the -4th, which I'm going to move to the bottom and make it an x to the +4th. And then I think this simplifies even more because this becomes what? -2 over 9 x to the 4th. And that negative can be in front, on top, bottom, wherever you want. Okay. So you've got a couple more here you can try on your own. If you have questions about them, we'll take a look at those in class. Okay. Sum and difference formulas. Another pretty straightforward rule. If I'm taking the derivative of two functions being added together, I just take the derivative of the first and add it to the derivative of the second. You just take the derivative of them separately. Okay. So for example, here's 2 already done for us. X to the 4th minus 2x to the 3rd plus x squared minus x plus 5. When they take the derivative, x to the 4th is just 4x cubed. The -2x third, the 3 times in to get -6. The x to the 3rd drops down to x squared. 8x squared becomes 16x, and -x just becomes -1, and that plus 5 becomes 0, so we don't have to worry about adding it at all. Same down here. We have this one. Actually, what they did is they foiled it out. They multiplied that exponent through. We did 2x minus 1 times 2x minus 1 times 2x minus 1. And when they did that, they ended up with this, 8x cubed minus 12x squared plus 6 minus 1. So we just have a bunch of functions being added or subtracted together. So I take the derivative of each part, and that gives me my derivative of the whole thing. Later, we're going to actually teach you how to do this one easier than having to multiply all those together. So this example here, if g of x equals this plus this minus this plus this, all we have to do is to find g prime, I just have to take the derivative of each part. So -x to the 6th, be careful of that negative. That becomes -6x to the 5th. And that 3 is my constant that just sits on the bottom. Plus 3x squared, the 2 drops down to become 6x to the 1st power. -4x, remember the rule here that this, again, this is just x to the 1. So when you multiply it down, all you end up with is a -4, and the 2 goes to 0. So when I rewrite this, I get -2x to the 5th plus 6x minus 4. Okay, so a pretty simple rule. Just find the derivative of each part and write them in order, and you end up with your g prime of x. Okay, let's get on to some more interesting stuff. What if I have two functions being multiplied together? So if it's asking me, remember when you see d over dx, it's asking you to take the derivative of whatever comes next. So if it wants the derivative of two functions being multiplied together, we have to use the product rule, which says that if I take the first function times the derivative of the second and add it to the second function multiplied by the derivative of the first. I don't like this notation, but it comes up this way a lot, and I don't know why that's the standard. Because of this plus, I like to just switch these places, and you'll see why in the next problem, in the next rule that we learn. But I prefer it to be f prime x times g of x, f prime times g plus g prime times f. I like it in that order better. I like to take the derivative of the first, times it by the second, plus the derivative of the second and times it by the first. In fact, this right here, I've heard calculus classes walking around singing that. Some of them like to use music, right, to help you remember stuff. If you want to sing that to help you remember the product rule, great. A lot of times we just shorthanded it and said f prime g plus g prime f. Okay, derivative of f times g plus the derivative of g times f. So putting that into action right here, h of x equals this function times this function. So this is my f and this is my g. Now you could FOIL this out and just use the sum or difference rule that we did in the last problem, but the product rule works as well. So what it says, remember, is f prime g plus g prime f. And ignore that my notation is very much not accurate in the math world, but it's just shorthand. So h prime of x is going to equal, I've got to take the derivative of the first function right here. So the derivative of 3x is 3. The derivative of this part, negative 2x squared, is negative 4x. So look, we're using the sum and difference rules right there. So I've got to take the derivative of the first, and then I've got to multiply it by the second, which is 5 plus 4x. I don't change it at all. I just multiply it by my second function. Then I have to add the derivative of my second function. The derivative of 5 is 0, of 4x is 4. And I multiply that by f, just my first function, which is 3x minus 2x squared. Now from here, you have a lot of options. At this point, you can FOIL this out, multiply this through, and try to simplify a lot of things. But again, on the free response, that's just a lot of places that you could maybe make a mistake. So that right there would be a great answer to me. On a multiple choice, they might simplify it. But on the free response, you would be okay with that answer. All right. The derivative of x times sine x. Well, we haven't learned the derivatives of trig functions. So really quickly, we're going to do this in the next video. But the derivative of sine x is equal to cosine x. So here's your quick mini lesson. The derivative of cosine x equals negative sine x. Okay, so those are two rules that you need to know for these next two problems. We'll actually go more in depth on those rules in, actually it's not going to be until unit 3 of this chapter. So I have the product rule. I'm taking the derivative of x times sine of x. So I take the derivative of my first function, which is x. The derivative of x is just 1. And I times that by my regular second function. So I just times that by g, which is just sine of x. And then I add the derivative of the second function. So I need to take the derivative of sine, which is cosine of x. And I need to multiply that by my first function, my f, which is just x. So when I rewrite this, 1 sine x just becomes sine x. And I don't usually like to have this multiplied by x at the end. I'll usually move it to the front because then you don't accidentally think that that's the cosine of x squared. And on top of that, this d dx, remember, this means take the derivative. Now that we've taken the derivative, I would say that dy dx, the derivative is equal to sine of x plus x cosine x. So when you see the y on top, that means you're looking at the notation of the derivative. The d by itself wants you to take the derivative. So be careful of that one. I don't know if we've talked about that yet. This one over here, 2x times cosine x. So there's a product rule right here. So we've got to worry about the product rule. This one, minus 2 sine of x, well, that's just a constant being multiplied by a function. So this part, we're going to be careful not to forget about, but that's just going to be our sum or difference rule. So let's start with here. Let's start with the product rule. So y prime equals the derivative of the first. 2x is my first. The derivative of 2x is 2, multiplied by the second, which is cosine of x, plus the derivative of the second. So the derivative of cosine x is negative sine x, multiplied by the first, which is 2x. And be really careful that you don't forget, that was just this part. Don't forget about the taking the derivative of our difference back here. So that becomes minus the derivative of 2 sine x is just 2 cosine x. And now we can simplify. So y prime is going to equal 2 cosine x minus, I'm going to move this 2x to the front with that negative so that I don't mix it up with my sine x. So minus 2x sine x minus 2 cosine x. Well, look at that. Those are going to cancel. Even better. So y prime equals just that middle part, 2x sine of x. Product rule, this is going to be a big one. We're going to use it all of the time. So whatever you have to do to memorize that. I don't care which form you memorize. If you're a singer, derivative of the first times the second plus the derivative of the second times the first, hum a little tune. If you can shorthand it, f prime g plus g prime f, great. Whatever you need to do, that's a formula that you need to have down. Which brings us to the quotient rule, which for some reason people don't like the quotient rule. They avoid it because sometimes you can rewrite problems to get rid of the quotient, and then you can just do the product rule or other things. For whatever reason, people don't like to use the quotient rule, but it works. I think it's more the algebra that they don't like dealing with. They like to get rid of this bottom fraction if they can. But what the quotient rule says, and here's why I changed the way I write the product rule. The quotient rule says if I have f of x over g of x, then I take, if you notice, here's the derivative of the first times the second, but instead of adding, I'm going to subtract the derivative of the second times the first, and I need to divide the whole thing by the second one, the second function, squared. Again, for those that like to do the little bit of a humming, how have I heard them do it? Nope, they say D high low minus D low high all over low low. So the derivative of the top, D high, times the low, minus the derivative of the low times the top, the high, all over low low. And like I said, this is one that you'll hear some students kind of humming, D high low minus D low high all over low low. Whatever you need to do to memorize it, just remember it's the same as the product, but a subtraction, and we divide it by our second function squared. Whatever's on the bottom, we're just going to square it. So, for example, we're taking the derivative of 5x minus 2 over x squared plus 1. So we could use the product rule, which I'll show you in just a minute. But since we're learning quotient rule, let's use the quotient rule. So what the quotient rule says is that I need to take the derivative of the top. So the derivative of, so my dy dx is going to equal the derivative of the top, 5x minus 2, which just becomes 5, multiplied by the bottom, the low, x squared plus 1. And then I'm going to minus the derivative of the bottom, which is 2x. That 1 goes to 0. The derivative of the bottom is just 2x times the top, 5x minus 2. And then I have to divide all of that by low. I have to divide all of that by just the bottom, the x squared plus 1 squared. So if I simplify this a little bit, I'm going to distribute that 5. So I get 5x squared plus 5. This negative 2x, I'm going to multiply by 10x. So that's going to give me, oh, not a positive. That's going to give me a negative 10x squared. And then the negative 2x I times by negative 2, and I get plus 4. And still, that's all over x squared plus 1 squared. So again, this right here on the free response test, that's a great answer. There's nothing wrong with that at all. On the multiple choice, you might not see this answer if they have simplified their answer a little bit. So just make sure you know how to simplify. You just won't always have to do it, if that makes sense. So this one here, 5x squared minus 10x, well, that's just negative 5x squared. And then my plus 5 and my plus, that's not just plus 4, that's plus 4x, guys. Don't let me make that mistake. So plus 4x plus 5. All over quantity x squared plus 1 squared. So this would be my dy dx. Now, I mentioned that you can get rid of the quotient rule by taking that bottom function. So if I just take the 5x minus 2 over x squared plus 1, this is just x squared plus 1 to the first power. If I move it to the top, so it's 5x minus 2 multiplied by x squared plus 1 raised to the negative 1. Now I have the product rule. I've got this multiplied by this, and sometimes that might be easier than using the quotient rule. It just depends on which form of algebra you want to work with. All right. So I think that's going to do it for this first part. We're going to continue with these rules a little bit more. We'll do some more examples in class, but let's wrap it up right there.